Good. So just a brief announcement. Next, on this Friday, you guys have a writing tutorial. It's at 2 p.m. There's only one tutorial this week at 2 p.m. and it's going to be in this room. So make sure you come, talk about sort of issues involved with preparing and presenting your DP2, and it's really important that you come and pay attention. So today we're going to continue our discussion of networking and network layering. If you remember last time, we talked about the three layers that are in any typical network stack. And these three layers we said were the end-to-end layer, the network layer, and the link layer. And we went through the example of how these three layers interact with each other as, say, a message is sent through the network. So on a typical sender node, we said there are these three layers. And there might also be a receiver node. And then there could be several, each time a message is sent through the network, it might pass through any number of intermediate gateway nodes or intermediate switches. So when a packet gets sent in, it gets sent through the end-to-end layer, in through the network layer, down into the link layer. The link layer chooses the next link to send the packet out over, sends it to one of these switches. The switch looks at the packet, sends it up to its own network layer, which is in charge of determining the next link that the message will take. And on the next hop, the message goes up to the link layer. The link layer determines yet another link for the message to take, or the network layer determines yet another link for the message to take. And then finally, the message reaches the receiver, or the message propagates up through the link layer into the network layer, and then finally to the end-to-end layer and out to the user. So we talked a little bit last time about various things that happen in this architecture. We said that there's this process of encapsulation that happens at each step along the way. So the end-to-end layer may attach headers onto the packet, and header and trailer onto the packet. The network layer may attach a header and trailer, and the link layer may attach a header and trailer. But at no point does any layer look at the data that a higher layer sent. And you also notice that in this architecture, what we've shown here is that only the link layer and the network layer of the switches that are forwarding packets are actually looking at processing the packet. So the end-to-end layer by definition is not involved in the forwarding of the packet. The end-to-end layer is only involved when one of the endpoints of the communication is involved. So what we're going to talk about today, we're going to finish very briefly our discussion of the link layer, and then we're going to turn and focus mostly on the networking layer. So you remember last time we got as far as saying that the link layer is in charge of a number of sort of important issues with the transmission of data across one link of the network. And we talked for a while at the end of class last time about this analog to digital, got that backwards, digital to analog to digital conversion. Well, we're going to talk about the other issue, though, that I said we needed to talk about in the context of the network layer, or the link layer, is the issue of framing. So the idea with framing is when you're sending a message out over a network link, the receiver on the other end needs to have some way of knowing that this is a packet is starting or a packet is ending, right? So, or as we call these packets when they're at the link layer, frames. So the issue with framing is to identify the sort of beginning and end of every one of these frames as it transmits over the network. And there's the sort of fairly obvious way to do this is, well, attach some special put some special symbol at the beginning and end of every packet. So for example, if we were looking at Ethernet, the payload of an Ethernet packet might contain the destination address, the source address, the type. So we'll talk more about what the type field means in a minute. The data and some checksum information that can be used to detect errors. And the preamble is a special code that is attached to the beginning of every one of these messages. And this is used to make the Manchester encoding, which you remember we talked about last class, which is used, this is used, sorry, to make allow the phase lock loop to lock into the message, which we talked about at last class. And it might be, you know, in the case of Ethernet, it's a sequence, a well-defined sequence 10, 10, 10, 10. But remember that with Manchester encoding, that the data that's actually transmitted out over the network looks a little bit different. And then following the preamble, there's this start of frame symbol. And then at the end of the message, there's this end symbol. So one thing we might be concerned about is, say, for example, what if the network layer tries to send a message that contains the end symbol in it? That would be a problem, right? Because then the end layer would have, you know, the end layer would have inadvertently terminated the message, even though this wasn't really the end of the message. This was just something that happened to be the same code as whatever the link layer had chosen for its end of code symbol. So, and the reason that this is a concern is, remember, we don't want the network layer to have to understand lots of details about how the link layer operates underneath it, right? The network layer shouldn't have to make any assumptions about what are valid symbols for it to transmit and what are invalid symbols for it to transmit. So the way that we're going to solve this is through one of two techniques. One, the first technique that we'll talk about for a moment is this idea of bit stuffing. I'll get to that in a minute. Another simple thing that we could do would be to simply use a code that can't possibly be generated by, say, for example, the Manchester encoding scheme. So if the network layer sends a message like 1111, the link layer is going to convert that into some sequence of ones and zeros once it applies Manchester coding. So if the link layer on the receiver sees a message like 11111, that can't possibly be a valid code that can't possibly be a valid message that could have been generated by the network layer. Only the link layer can actually send that sequence of bits out. So we could tell that would be a terminating symbol. Another simple way, though, to send one of these end codes is using this technique called bit stuffing. And the idea is pretty simple, and it's kind of a neat technique that can be used in general when you have to send when you have to do this kind of encoding at a lower layer. So the idea is, suppose we set our end code was equal to some bit string like 1111. And the solution in bit stuffing is very simple. What it says is that when you receive a sequence of bytes or sequence of bits from the network layer at the link layer, it says that you should convert any sequence of bytes that look like 111, 3 ones in a row, into 3 ones in a row followed by a 0. So this happens at the sender. And then the receiver just reverses this. It says any sequence of 1110 gets converted to 1111. Okay? So you can see that this means that, and this transform is only applied to the payload of data packets that is coming from the network layer down into the link layer. Okay, so you can see that there's no way for the link layer now to send the sequence, or for the network layer to transmit the sequence, to actually cause 4 ones in a row to be sent out over the wire because of this transformation. So if the network layer tries to send a message that contains a sequence with 4 ones, what the link layer is going to send is 3 ones followed by a 0 followed by a 1. Notice, however, that this also means that every time if the network layer tries to send a sequence of 3 ones followed by a 0, the link layer will transmit 3 ones followed by 2 zeros. Okay? And then we can just, at the receiving end, we can just trivially apply this reverse transformation. So this idea of bit stuffing allows us to send these to specially transmit these, to guarantee that any time that the link layer on the receiving side actually sees 4 ones in a row, this is really the end symbol as opposed to the network layer trying to transmit 4 ones in a row. Okay? So that's all I want to say about the network layer, or about the link layer. And what I want to do now is move on to a discussion of the network layer. So the network layer has 2 primary functions that we're going to talk about today. The First one is forwarding. And the second is routing. So the idea with forwarding is as follows. Suppose that we have some, so the idea with forwarding is basically to allow nodes to decide where they should send, given a particular packet, to allow them to decide what the next hop for that packet should be by looking at the destination address that's in the message that they're trying to transmit. So they're going to look at the destination address and then make some decision about where to send this packet next. And they're going to do that by keeping a table that basically maps every address into the next link to send that, the next link to send to. So let's look at a really simple example. Suppose we have 5 machines, A, B, C, D, and E. Connected as follows. And let's number these links. Let's number this link from E to B. We're going to call it L1. We're going to letter this link E to D, L2. And then I'm going to number all the links sort of in the same way. So B's link to A, I'll number L1. B's link to D, I'll number L2. And B's link to E, I'll number L3. So notice that this link has, I've given 2 names to this link depending on whether we're talking about it from the perspective of B or E. Okay, so now we can do the same numbering for all of the other links. So call this L1, call this L2, call this L3. And this one is L1, L2 from C's perspective. And this is L1 and L2 from A's perspective. So now we have this labeled graph here. And now let's look and see what the forwarding table for one of these nodes might look like. So for example, if we look at the forwarding table for node A, what we'll see is one entry for each of the other nodes that are in the network. And this entry will tell us, given a message destined for this, whatever address is in, this is the destination address. So given a particular destination address, it'll tell us what the next link we should use is. Okay? So if A, so when this is the forwarding table for a particular node. So in this case, we're looking at the forwarding table for node A. So if A sees a node destined to node A, what should it do with it? Well, it's destined to its local node, so it's going to do the obvious thing, which is send it up to the end-to-end layer. So I'll just write E to E. So if it receives a node destined for B, it's going to say, okay, it's going to compute, it's going to, presumably it wants to send it along whatever the shortest path is. And we'll talk about how the next step, routing, is actually deciding which things should be there. But for example, it might have L2 as the next link. Okay? And if it wants to send to C, it might have L1 as the next link. So A to B is using L2, and A to C, it's using L1. Okay? Now, node D is going to, so if it wants to route to D, it's going to have to route through either B or C. And so for now, let's just say it routes to L1, and then it's going to, so it routes to C, and then it's going to allow C to go ahead and forward the packet on to D. And if it wants to route to E, well, it can either route through B or through C, but let's say maybe it wants to route through B because it has a shorter path. So we'll write L2 here. Okay? So this is just a very simple example. Now you can see that any time that A wants to send a packet, it has a next hop that it should use for every destination address within the network. So this is very simple, and this is sort of at a high level, the way that forwarding works. Of course, there are some other details associated with getting forwarding to work properly. In order to talk about sort of how forwarding actually works at the interaction between these in the interaction between these layers, what I want to do is just give you some examples of what the packet headers look like for different kinds of protocols that are used in the real world. So we're talking about here, this is the IPv4 header. So remember, IP is a protocol that runs at the network layer. And this header has the following information in it. So what I've shown here down the left side is a sequence of words. So these are 32-bit 32-bit words, and then I've just broken up the bits by number along the top. So The first sort of word has it has information about the version of the protocol that's running in it. So in this case, the version would be 4 because this is IPv4. There's a new IP protocol that is being in the process of being deployed called IPv6, which you'll sometimes see referenced. There's a header length field, just specifies the length of the header. There's a TOS field, this is type of service. It's typically not used in most packets. And then there's a packet length, which is the entire length of the whole packet, not just the length of the header. So this is should be fairly straightforward, except for the type of service field, which you guys don't need to pay any attention to. So the next field is there's this identification. The next word, has identification, flags, and fragment offset. Let's just look at the next one. And the next one has time to live, end-to-end protocol, and checksum. So the important fields here, I'm blanking on what the identification field contains, which is why I'm stalling. But the identification field, so there's the flag. So let's just talk about the other fields, and we'll come back to identification if I remember it. So the flags field the flags field simply contains some information about whether this packet has been fragmented or should be fragmented. So fragmentation is something that this packet can be split into multiple sub-packets. You don't need to worry about it too much. And the fragment offset says if this packet has been split into these sub-packets, these fragments, then this is the number of the fragment that's being transmitted. So the interesting ones now come in this next row. So we have the time to live flag, the end-to-end protocol, and the checksum. So the time to live flag, the time to live field is sometimes abbreviated TTL. And it's time to live is a little bit of a strange name for it. Basically what this says is as this packet is being forwarded through the network, we're going to decrement the time to live by 1 on every step that it's forwarded through the network. And if the time to live reaches 0, we're going to stop forwarding this. So the reason we care about time to live is that there can sometimes be routes, there can sometimes be loops in our forwarding graph. So suppose that we had set this up so that A sent messages destined for, say, E to C, A sent messages destined for E through C, and C sent messages destined through E through A, right? So that would be a loop, and that would be a problem. So we're going to try and avoid forming these loops when we do our routing protocol, but there are going to be certain situations when nodes fail, for example, that loops can occasionally occur, and we're going to use the time to live field to eliminate those. The next thing is the end-to-end protocol. So the end-to-end protocol is a specification of the which end-to-end protocol we should forward this message onto. So I'll talk about that more in a second. And then there's this checksum field, which can be used to determine whether the message was fully formed. Although it turns out that in most cases in IP, this field probably isn't used. So and then there's a source address and a destination address. So these are IP addresses that identify the endpoints of the packet. And finally, there's some additional optional information which can specify a huge range of different things. It can be up to 44 bytes. In this case, you don't need to worry about it. And then finally, there's the payload, which is the actual message that was sent from the end-to-end layer into the IP layer. So what you see happening here, if we look at a diagram of what the interface between the end-to-end layer and what the interface between the network layer and the link layer is. So we have let's just look at our 3 layers again. We have our end-to-end layer, we have our network layer, and we have our link layer. And one of the things that we can pick out here is that notice that we have this end-to-end protocol that's actually in our IP packet. So what this means is that if I have a network protocol like IP that's running here, when it receives a packet destined for its local address, say destined to itself where it's supposed to forward it up to the end-to-end layer, it can actually dispatch this packet to a number of different end-to-end layers. So for example, we talked last time about the TCP protocol, but there are a number of other end-to-end layers that can be used in the internet. So we'll talk in this class a little bit about a different protocol called UDP. We'll talk about this more, we'll talk about the end-to-end layer more next time. But the point is that this up call to the layer above us is controlled by the contents of this header that we have. So similarly, if we look at the contents of, we look at an Ethernet header, what the Ethernet header has on it is the destination address, which is 48 bits, and the source address, which are 48 bits, followed by a link protocol. So the link protocol says, and so the Ethernet, remember, is a link layer protocol, and what happens is, so if we have Ethernet here, it has a protocol ID that specifies the protocol that it's supposed to send messages back up to. Okay, so these fields, these link protocols. So the one question you might ask is, well, how does the Ethernet layer know which link protocol it should send its messages to, or how does the network protocol know which end-to-end protocol to send its messages to? So it's kind of interesting, and it's worth looking at the pseudocode for these for one of these protocols just quickly in order to understand this a little bit better. So let's look at the pseudocode for the function called, we're going to call NetHandle, that accepts messages from either from the end-to-end layer to be sent out across the network, or from the link layer when a message is sort of received as it's forwarded through. So we can use this procedure both for down calls and up calls. And it accepts a packet, which, say, for example, has this format that I've shown here, which is the same as the format I showed on the other page. So the first thing this is going to do is it's going to check and see if the destination of the packet, for example, is the local address. And if the destination of the packet is the local address, then we know what we should do with it, right? We're going to pass it up to the end-to-end layer. And we're going to decide, we're going to send, so what we're going to do is we're going to de-encapsulate this packet, right? We're going to strip the header off of it. So we're just going to send the payload up to the layer above, but we're going to need to dispatch to the appropriate layer, which we're going to do by sort of saying, naming what the end-to-end protocol is that we would like to dispatch to. Okay, so, and there may be some other options that we pass along with this as well. So that's what the 3 dots there mean. So now, if this isn't for the local packet, then for the local node, then we need to send this packet out again, right? So what we're going to do is we're going to check the time to live on this packet. And if the time to live is greater than 0, then we are going to decrement the time to live. If the time to live is less than or equal to 0, then we know that this packet, we're not going to forward this packet anymore. We're just going to drop it. So the time to live gets set initially by the first guy who sends the packet out. He initializes it to some value, which is the maximum number of hops that he wants this message to be propagated for. And then, so after we decrement the time to live, we're going to look up in our forwarding table the next link that we want to use. Okay, and what I've shown here is that we're going to look up not only the address, we're going to look up the sort of protocol to use and the address for the next, and the name of the next link. So, for example, this IP layer might have Ethernet underneath it, which might be one protocol, but there might also be a Wi-Fi layer that's here that we could also send messages out. So we could send out through either one of these things, through either one of these protocols. So we look up the one we want to send out, and then we call this link send routine, which actually does the transmission out over the appropriate named link. Notice now what I've specified, I have this net prot in all caps here. So in this case, this should be, for example, IP. It's the name of the network protocol. So when the network protocol sends the message to the link layer below it, it specifies what the network protocol is that it wants to have returned, that it wants to be called on return. So it says, please, link layer, when you have received a message that needs to be sent up to the network layer, dispatch it to the network layer named netprot. Okay? And then, of course, if there's an error, if, for example, the TTL, we can't transmit the message out, if TTL has expired, if we've sent it too many hops already, then we're going to need to do some kind of error handling. In this case, error handling might be send a message back to the source address of this message and tell them that the TTL ran out on this message. That would be one thing you could do. Another thing you might do is simply drop the packet or ignore the error. Okay, so this is just a simple example of how forwarding might work. And what I wanted to use it to illustrate is the fact that there can be multiple different link layers at the bottom that can be dispatched to. And these link layers can, in fact, dispatch up to multiple different network layers as well. So in today's internet, it's uncommon to see you'll rarely interact with anything that's not using IP at some layer or some network layer. But there have in the past been a variety of different network layers that have been proposed. You guys may have seen an old protocol from Novell called IPX, or you may have used AppleTalk, which is an Apple protocol that in some varieties also runs at the IP layer. Finally, I just want to point out that the last little layering detail that I want to get to is that if you think about what these link layers are, think about the link layer from the perspective of the network layer. The link layer is simply one, the link just looks like one hop to one more connection. But in fact, these links can themselves be networks. So that's kind of a weird statement, but here's a simple example of what I mean. Suppose that this link layer, that there's one of the link layers that the IP layers can send a message to is a modem connection, okay? But if you think about what a modem connection is, right, it's a connection out over a phone line. And a phone line is itself, right, as we talked about at the beginning of the class, a phone line is itself a kind of a network, right? It's this circuit switched thing that goes through multiple ones of these circuit switches as opposed to going through these. So underneath the modem, the modem layer, which looks like a link to the network layer, there's actually some more sort of, these link layers can actually themselves be composed of a number of links. And they can themselves be a type of a network. So it's sort of worth realizing that there's a kind of a hierarchical relationship that that the link layer may actually itself be a network consisting of multiple links. But from the point of view of the higher level link layer here, it's just a single link, a modem connection to some endpoint that we can send a message over. Okay, so what I want to do now is take you through, we're gonna switch gears a little bit and talk about the sort of next piece that I said that we needed to address, which is this issue of routing. So I said we're going to talk about forwarding, then we're going to talk about something else called routing. So routing is the process by which we build up our forwarding tables, okay? So what I showed you here was I just sort of told you what the values that should go in these forwarding tables should be, but I didn't tell you how they're derived or where they came from. So in this case of this simple network, it was relatively easy for us to, by hand, sort of come up with a set of possible forwarding paths that seemed reasonable. But you can imagine that if this network had scaled up to 1 million nodes, that's not something that we want any individual to have to do. No person should have to configure all these routing tables. So instead, or all these forwarding tables. So instead, what we're going to do is we're going to use this process called routing in order to build these forwarding tables automatically. And what we really want our routing protocol to be 3 things. First, we want it to be scalable. And the obvious way in which we want it to be scalable is the way that I just said. We don't want to have to have people, we want this thing to scale up to, say, 1 million nodes or several million nodes and be able to continue to work. We shouldn't have to have people sort of involved with configuring, building up these forwarding tables at every step of the way. We also want it to be robust. So by that I mean it should be tolerant of faults. If a node fails in the network should eventually discover that that node has failed and be able to forward packets around the failure or be able to compensate for the failure if at all possible. Finally, we want this routing protocol hopefully to be distributed. So we don't want to have one machine that's responsible for setting up the forwarding table on all the other machines. We don't want to have one machine that needs to contact all of the other nodes and collect information about what all of their links are and assemble all those links together into one global forwarding scheme. And this really gets at the scalability again. So what I want to do is to take you through the process of routing. Before I do that, I just want to take a quick digression. We're going to start off with very tiny networks in this, and just talking about a very simple baby network. But just so that you guys don't feel like this is completely unrealistic, I want to show you that, in fact, the internet at some level started out like this too. And what we're going to do in the course of this class is sort of build up from these very simple networks that maybe look the way the internet did at first to the schemes that are more like what is actually used in today's production internet. So, sorry, I went back on you guys. Okay, so this is a picture of what the internet looked like in 1969. So you may not be able to read the labels on these things, but we're looking at 3 nodes here. This is UC Santa Barbara on the coast of California. in sort of central California, or southern central California. This is Stanford Research Institute, SRI, which is the Bay Area. This is Utah, and this is UCLA. So this was the ARPANET, which was a precursor to the internet. It was sort of one of the very first of these large networks that spanned, large wide area networks that was ever developed. And each of these little square nodes here is a machine that's on this. So there were 4 machines on the ARPANET in 1969, and there were these 4 routers that were being used. So this is 1971. So by 1971, there still is a cluster of these machines in California, but you notice that Illinois, Carnegie Mellon, and Boston have suddenly appeared on this map. So MIT is here, Lincoln Labs is here, Harvard is here, BBN, which is another large company that does a lot of networking research in this area, is here. So the network has started to evolve, and in particular, you notice that there are now these sort of 2 clusters, these 2 regions, one on the West Coast and one on the East Coast, that have a number of nodes. So it just keeps growing and growing. So by 1980, you see the network has gotten substantially larger. And one of the interesting things about this is you're starting to see a diversity of links. So notice that Hawaii is now connected into California by way of a satellite connection, as is London. So we now have not only just these wires that are running, but in fact we have wireless links. But we're still on top of this. At the same time this was happening, all the protocols we've been talking about were being developed. And one of the whole goals of this was to be able to support these multiple different kinds of links on top of a standard networking protocol. Okay, so by 1987, this thing has really turned into a number of decentralized networks. There's this large network called the ARPANET. There's something smaller called the NSF backbone, and a number of other networks that are military networks and so on. These are all connected together, and they're all being, by 1987, they were all running this TCP/IP protocol that was being used to exchange information between all of these things. So around about a few years after this, right, the internet, the sort of World Wide Web suddenly happened, and there became this huge commercial interest in the internet. And that has really sparked this explosion of nodes and made the network just huge and incredibly vast. So it's hard to see this, but at the middle of this, you notice that there's a little orange node here. This bar on the left side is showing the out degree of the nodes in the network. So this number is 2977. So that means there's a node at the center of the internet that has 2,977 links to other nodes in it. Okay, so this is a really incredibly large network. And you notice that all of these, 20 or 30 bright pink red nodes here have hundreds to thousands of outgoing connections on each one of them. So there's this core of the internet that is very highly connected to a very large part of the network. And now out around the edges are these much smaller networks that have much lower connectivity. And these are things like service providers, for example, that consumers might pay some money to get a connection from. So this is the sort of core of the internet. These are the people who are not so much the end users on the internet, but the service providers that are providing connectivity for the end users. Each one of these little nodes represents one of those service providers. This was as of 2003. Okay, so what I want to do now is to start, as I said, we're going to sort of start off with a baby version of a network. In particular, we're going to look at how forwarding or how routing might work in this very simple network that I've shown here. So let's see what happens. So we're going to use a protocol that we call path vector routing. And the idea behind path vector routing is that we're going to build up the paths from, that is, the sequence of nodes that we should forward messages through in order to reach a particular destination. And the way that this is going to work is through we're going to have 2 steps. So let's put it over here. So routing is going to consist of two steps. An advertisement phase, or an advertisement step, and an integration step. And the idea is that during the advertisement step, each node is going to advertise what other nodes it knows how to reach. And then during the integration step, each node is going to take all of the advertisements that it heard during the previous advertisement step and integrate them into a new set of routes that identifies the new set of nodes that this node can reach. Okay, so this will be very, very clear when I show you the example. So let's just look at the case of all the nodes figuring out how they can reach node E. So what's going to happen is that first node E is going to send out an advertisement that says that node E knows how to reach node E, right, which it obviously does. And the way that it reaches node E is simply by forwarding a message up to its end-to-end layer. So it says to reach node E, come this way, and it sends it out over the 2 links that it has to nodes C and D. So when nodes C and D hear this advertisement, during their integration step, what they're going to do is to add this information about this connection to node E, and they're going to store which link it is that they send that message out over. They should send messages out over in order to reach node E. So in both, node C is going to store link 1, and node D is going to store link 2. But in addition to that link, they're going to store the path that they use. So now what's going to happen is that each of C and D is going to, during the next advertisement step, C and D are going to also advertise the information that they have about the links and the nodes that they can reach in the network. So I'm only showing the advertisements for node E here. But of course, at the same time, C and D are also advertising the fact that they can reach themselves and maybe their ability to reach other nodes in the network that we haven't shown. So we're just looking at E, but bear in mind that all the advertisements are being done for all the nodes at the same time. So C sends out an advertisement that says, I can reach node E, and the way to do it is to send through, and I can reach node E via C and then E. And similarly, D sends out a message that says, I can reach node E via D and then E. So, okay, so up to this point, we haven't really seen anything very interesting. But now during the next integration step, we see that these 2 nodes, B and A, now have heard an advertisement that gives them a path that allows them to reach node E. So now every node has a path that allows them to reach node E, but this advertisement and integrations process is going to keep going on. So for example, nodes A and B are going to advertise that they can also reach node E to their neighbors. And in this case, it's probably unlikely that either any of the nodes would like to switch to a new route. So for example, it's not clear that there's no reason, for example, that A would want to forward its message. It's probably unlikely that A will want to forward its messages through B to reach E, right? Because it's going to be a longer path than for A to send its messages simply through C and then to E. But B doesn't actually know whether or not A knows about E yet or not, so it needs to continue to broadcast this information out. Well, this is pretty simple, and it's pretty clear how this works. And once this process has been running for a while, you can see that the network is going to converge into a state where every node has a path. As long as the network is connected, it'll converge into a state where every node has a path to node E, right? And the amount of time that it'll take for that to happen is equal to sort of the number of hops, the maximum number of hops that any node is away from node E. So once this node has converged, now we can trivially build up our forwarding table simply by pulling out the link number from each one of these nodes. So for example, we can see that E's forwarding table simply says to reach node E, you send it to my end-to-end layer. D's forwarding table would say to reach node E, you send it over my link L2. C's forwarding table would say to reach node E, you send it over L1. B's forwarding table would say to reach node E, you send it out over my L1, and so on, okay? So once we've done this path vector routing, at the end of this process, we will know which links, we'll have built up the forwarding table that we can use for sending our links. Okay, so this is this very simple process, but now let's look what happens when something, so what we said here is just at each advertisement step, we're going to, after each advertisement, we're going to go ahead and do integration. Integration, basically what we're going to do is we're going to try and pick the best path in some way. What we've shown here is simply picking the shortest path. So we've picked the shortest possible path for every node to reach node E. And in case it wasn't clear, I didn't explicitly state this. It's important to realize that nodes are going to ignore advertisements with their own address in the vector. Okay, so if, for example, when node E hears node D advertising that it can reach node E is going to say, oh, well, I am node E. I don't actually need to pick up this path. I don't need to send my packets to myself through node D. That would be a silly thing to do. And that would create a routing loop, which is something that we presumably don't want to do. So this is a simple way, using these path vectors, we can use to avoid creating routing loops. Okay, so now let's look at what happens, something a little bit more interesting. Let's look and see what happens when, for example, there's a failure. So this is just exactly the same network that I showed you. But suppose, for example, that the link between D and E fails. Okay? So now the network no longer has, now node D no longer has a route to node E. But remember, the way that I described this is that this advertisement process is just going to continue going on in the background, right? So what's going to happen is that at some point, node D is going to realize that its link to node E went down. And node D is going to cross this table out of its entry. So node D is going to basically stop hearing advertisements from node E. When it stops hearing advertisements from node E, eventually it's going to do something. It's basically going to expire that entry from its link table. So after it hasn't heard advertisements from node E for a while, it'll expire that entry. And then sometime later, it will hear an advertisement from node C saying, I know how to get to node E. And now node D can go ahead and integrate this new path into its routing table. Now notice that this process is just going to propagate through the network. So once node D stops hearing advertisements for how to reach node E, it's going to stop sending advertisements for how to reach node E. And so similarly, we're going to, because B is also routing its information through, had previously been routing its packets to reach node E by way of D, it's going to say, oh, well, I stopped hearing about this route DE from node D, so I'm going to stop using this. And instead, then sometime later, it's going to hear about this new route, DCE, and it's going to integrate that into its table. So it's this process where there's this sort of process whereby nodes continually advertise and integrate routes. And we talked about this, and there's this sort of interesting thing which happens, which is that nodes forget about routes that they haven't heard about for a while when they miss an advertisement. So this forgetting about routes is an important sort of principle that's often employed in networking called soft state. The idea with soft state is that you should only keep information when that information gets refreshed. So all the information that you have has some time limit on it, and when you haven't heard that information refreshed after some time limit, you throw it out. So that's what we're doing with the routes here. And we only keep routes that we've heard advertised recently, basically. And that has this nice property that it allows us to adapt to faults within the network, right? So we saw a failure happen. We saw that sometime after that failure, this soft state property would cause the information about the link between D and E to disappear from the network, and then nodes would rediscover their new links that allow them to connect to node E. Okay, so what I want to do now, so this is sort of the basic process, and path vector routing is fairly similar to the way that routing in the internet actually works. Next time you guys for next time in recitation, you're going to talk about a protocol called the Border Gateway Protocol, and you're going to actually study in much more detail how internet routing works. But this is a nice simple model of how routing in a small network might act. So the problem with what we've discussed so far, move over here, is that if this is a very large network, these number of routes that you're going to have to hear about is really huge, right? So suppose that this, instead of being a 5-node network, was a 1,000,000-node network. Well, now I'm going to have a million every node is going to have a table that's a million entries long, right? That's going to be really big. And it's going to have to hear a million advertisements. And every time there's a failure, well, that's going to be a pain because we're going to have to wait for that information about that failure to propagate through the whole network. So in some sense, this simple path vector routing protocol we have doesn't really meet the scalability goal that we want to scale this network up to a very large size. So we have an issue with path vector routing and its scalability. Okay, so the solution is a solution that is often used when we have a scalability problem in a computer system. It's hierarchy. Okay, so let's see what I mean by that. So you remember when I was showing those pictures of the internet, there are these different kind of sub-networks that were forming over time on the West Coast, on the East Coast, or there was the ARPANET and the NSFNet and the MILNet that were these sort of different networks that were all a part of the internet as a whole. But they were these sort of different regions that were separately administered and that often corresponded to a specific organization like the NSF or like the military. So oftentimes these regions, so it's very common when you look at any network to see to have these kinds of regions in them. So for example, there's a network that is MIT's network, right? And there's, Harvard, for example, has a network that's Harvard's network, right? And those two things are sort of logical regions that define define different parts or different groups within a network. So if you were to look at any network, you would see it sort of almost any large network is organized in this way, into these regions. In the paper next time, we're going to call these regions autonomous systems, or ASs. Okay, so autonomous as in sort of operating on its own, operating without being dependent on the other parts of the system. So for example, if MIT's internet connection went down, connection to the outside world went down, that wouldn't stop you from being able to connect to machines within MIT, right? So MIT is autonomous in the sense that it continues to operate in the absence of its connection to the rest of the internet. So let's look at a simple example of a network that has this hierarchy property and see how we would modify the routing algorithm that I just talked about. So suppose I have two small networks, each with 3 nodes in them. Let's call them A, B, C, and D, E, and F. Okay. So these are each going to be autonomous systems, which I'll draw by drawing a circle around them. Okay, so one way we could do routing would be to do what I had shown before, which is that each node within, say, this autonomous region, which I'll label 1, or autonomous system 1, and this one 2, would have information about all the other nodes everywhere else in the network. But that has the scalability problem that we mentioned. So instead what we want to do is we want to make it so that only a few of the nodes in here have to, so that we don't have to have information about all of the nodes that are anywhere within the network. We only have to know about a few nodes that we say are on the edge of each one of these networks. So the idea is as follows. Suppose these are connected in this way. And what we're going to do is we're going to appoint one node within each one of these regions. For example, it could be several nodes. One of these regions to be a so-called a border node that sort of sits on the edge of these two regions. And we're going to connect just those two nodes together. So we're only going to have one link, but we're only going to have a small number of links between our two ASs. And now if we look at the forwarding table for one of these nodes within, say, AS1, it's going to look as follows. So what I'm going to do is I'm going to write the addresses for these different ASs as hierarchical addresses. So we're going to call node A's address 1.A, and we'll call node E's address 2.E. Okay? So what our forwarding table looks like is a list of addresses and then a link to use. Okay, so this is going to be the forwarding table, again, for node A. So A is going to have it's going to have an address 1.A in it, and the link to use in that case we've already said is end-to-end. Okay, it's going to have an address 1.B. So to get to B, A is going to route via this link here, which let's call this link number 1. Okay, so it's going to route to link 1, and it's going to have a connection to 1.C, which is going to route via this link here, which let's label that 2. Okay? So now what we want, though, now we don't have any information about how to reach network 2. So what we're going to do is rather than storing information about every machine in network 2, we're going to store just information about how to reach the edge of network 2 and then trust that network 2 is going to be able to route to anybody whose address begins with 2. So what we're going to do is we're going to say 2.star, right? 2.everybody. So where star is the character that says anybody whose address has this prefix 2 dot. So anybody whose address has prefix 2 dot, we're just going to send to node C. So we're just going to send that over link 2. Okay? And so similarly on the other side, we're going to have a table. Each of these nodes is going to have an entry 1.star that specifies that it should route messages for network 1 through node D. Okay, so you see in this way, now what we've been able to do is to make it so that each one of these autonomous systems, sort of each node only knows how to route to other nodes within its sort of group, and that in order to cross groups, you route through one of these special sort of border routers or border nodes. Okay? And we're going to talk about the way that this border routing protocol actually works in the internet next time in recitation. But you can see that what we've done is we've accomplished we've accomplished this sort of hierarchy, so we can make the system. We've made these tables much smaller by including these star entries in them. It's worth just mentioning as a final caveat that we have given up something by doing this. Okay, what we've done is we've forced every node that is within one of these regions. Now, if this node's address, in order for this node 1.a to be able to continue to operate, it can only be within connected to somebody like C who can advertise information about all the nodes whose name begin with 1. So if 1.a, so we've basically forced this sort of network to have this, by imposing this kind of a hierarchy on the network, we've limited to some extent the ability of these nodes to move between networks, because node A can only be advertised by way of node C. And this, so in the internet today, there's actually multiple layers of hierarchy. So you may have noticed that internet IP addresses have the form A.B.C.D. Those are so that's a 4-layer hierarchy that we have in the internet. You guys will learn more about this on Thursday in recitation. And what we'll do next time is talk about the end-to-end layer and enforcing eliminating some of the limitations of the best effort network.